Okay, so for today's lesson, we're taking a look at this material, and so it's 5/8/24. In case you're gone and you need to see this video as a lecture. All right, so let's take a look at solving some wave problems. We were starting these things yesterday, but we did not quite finish it. So the demonstration I did with you guys at the beginning of the class is talking about the speed at which particle or waves travel dependent on the medium properties. And so we know that sound travels much more efficiently through solids than liquids than in gases. Okay, let's move into the wave speed equation. If memory serves, I did go through a couple of these things with you yesterday, correct? Okay, just for recording purposes, I'm just going to reiterate this really quick. I'm going to do it quickly since we did through these yesterday. I want to find that wave speed. Again, we said that was frequency times wavelength. I multiply those two numbers together, 512 hertz. And someone that has the answers for me, please refresh my memory on what these things are. So we did this yesterday. 340 meters per second. Okay, so we did that problem yesterday. That's just to revisit what we did. All right, now if the speed is the same as calculated, what's the wavelength of that sound? We know that the wavelength should double because the frequency is halved, right? And so that's the same basic idea that we looked at yesterday. What I would like you guys to do is I would like you to consider the questions that are based on this diagram. So we talked about amplitude, we talked about wavelengths and things like that. This simulation, you guys will get to use this simulation for a standing waves lab. Probably do that on a Friday. By the time I think we'll be there. But take a look at those measurements. You have a ruler here that's along the vertical axis. You have a ruler along the horizontal axis. And you have a waveform being generated. What's the amplitude? What's the wavelength? And then what is the speed of that wave? Why don't you try those three? Okay, once you have those numbers, will you please tell that person that you're sitting next to? See if you guys are in agreement. What's the amplitude of that wave? What's its wavelength? And what would be that speed if the oscillator set it to it? Take them off, talk it over. Ashley, which one did you say not to eat off of? Amplitude. Help me out with that one. I heard it. Don't be shy. Say it out loud.
1.5.
Thank you. One more time.
1.5.
Most common mistake. It's not the peak to peak value.
So it's half.
It's the maximum displacement from equilibrium. So when I go to do this one, and Simon, I'm glad that you made that mistake. We learn a lot from mistakes, right? So the amplitude is that measurement, or this measurement. It is not a peak-to-peak value. Maximum displacement from equilibrium. Would you guys agree that the equilibrium position is right here? So the amplitude would be half that value. So if you said 1.5 or 1.6, it'd be more like 0.8. Say it again.
1.75.
Yeah, that's okay. We can split hairs on that, but it's half of the peak-to-peak value. So roughly in the neighborhood of 0.75 to 0.8, and this would be 70. Okay? How about the wavelength? What parts of that wave are you looking at there, Simon, to be able to get to that 3?
I looked at downward.
Yeah, use the terms that we looked at yesterday. So this is meant to re-hit some of those terms, vocabulary terms. Were you looking at the bottom of these graphs? Were you looking at the top of the waveforms?
I was looking like right on the equilibrium where it's going down.
Okay.
On the top. I just did that, and then the second time I did that.
So you looked like here to there?
Yeah, I assumed that any two corresponding
Absolutely.
dots would work.
And it's a fair assumption because a waveform or wavelength is a repeat distance. And so I could take crest to crest, right? That's the term I was looking for. I could go crest to crest. I could go trough to trough. You cannot go equilibrium to equilibrium. You guys notice that it goes through equilibrium twice? So if I'm going to do this as a wavelength, I have to skip over one of those equilibrium positions. But it doesn't matter whether or not I go crest to crest, trough to trough, or they're the same length, right? So what did you say it was again, Simon, about 3?
A little over 3.
Let's call it 3 centimeters. And let's call this 0.8 to make the math easier, okay? So if I use the wavelength to be 0.8 centimeters and the wavelength to be 3 centimeters and the I don't need the amplitude for wave speed, do I? What is the speed at which that wave propagates? So the stuff that we looked at yesterday. So I need the frequency and I need the wavelength. You just multiply them together. Thank you. Yeah, it's 6 what? So I'm going to write this down. Velocity is equal to frequency times wavelength. It is a 2 hertz frequency, and the wavelength is 3 centimeters. I multiply 2 by 3, I get 6, and then the units would be per second, centimeters per second. So what that would mean is that that wave would be traveling at about 6 centimeters per second. Okay. Now that simulation is here. I'll show it to you, and just so you can get a sense of that. While I'm getting this thing pulled up, will you take a moment and tell that person that you're sitting next to what would happen to the wave speed if you tighten the tension? So I make that tension greater. I tighten the spring, if you will. What would happen to the wave speed? While I'm doing that, pulling this thing up, you talk that over. What would happen to the frequency, or what would happen to the wave's wavelength? Take a moment and talk that over. Okay, this is the simulation showing an oscillator going up and down, similar to my hand, going back and forth. It's producing a sinusoidal waveform. The frequency we said was 2 hertz, correct? Yeah. Okay, so again, I'm trying to get that set up to be around there. I'm going to make that tension a little bit. I'm going to make that tension a little bit lower to begin with. And the wavelength, we could do all that. But what happens if I increase the tension? What should happen to the speed? It should go faster. And the reason for that is I've increased the restoring force, if you will. So if I make that tension bigger, you'll notice that the speed at which it propagates increases. Can you see the speed go up? What happened to the wavelength? You guys see the wavelength got greater as well? Okay, so the material properties of that medium will affect things like wave speed. And of course, the wavelength depends on how fast it's traveling. If I make that tension even lower, what you'll notice is that it hardly moves at all as it's moving along there. Can you guys see how slowly it's propagating now from left to right? So the speed is again dependent on the material properties. If the speed is constant, then increasing the frequency will do what to the wavelength? Speed is fixed. What happens when I increase the frequency? Short. It will make the wavelength smaller. And you can see that a higher frequency produces a shorter wavelength when that speed is constant. When I make the frequency lower, that would do what to the wavelength? Make it longer. And you can sort of see how that works. Okay? All right. You guys will be doing some work with the simulation so you can see how the wave speed stuff works. I'm going to save that for probably Friday. Is the day I'm looking for that. Okay? Questions for me? Okay, I'm going to stop this thing here, the video, and I want you guys to have some time to work on some of these problems yourself. And so I'm going to put a clock up here for you about 8 minutes. That should be plenty of time to be able to get through and work through that.